Dear students, now we are going to discuss TE waves in rectangular waveguide and derive its field equations. TE means transverse electric. So here TE waves are the waves in which the electric field is entirely transverse in the direction of propagation. If the wave is propagating in the z direction, then Ez value becomes 0. That means that electric field is entirely transverse in the direction of propagation. But the TE wave has the magnetic field in the direction of propagation. That's what given here. For TE waves in rectangular waveguide, Ez is equal to 0, Hz is not equal to 0. So it is having the Hz component. So first we are going to find out this Hz component in this TE waves. So here the field components of TE waves can be determined by solving the EM wave equation. So here we can consider the wave equation in a rectangular waveguide in terms of magnetic field. That means del squared Hz is equal to minus omega squared mu epsilon Hz. Okay. So here we can consider the direction of propagation as Z. Okay. So here del squared is nothing but squared Hz by dou x squared plus dou squared Hz by dou y squared plus dou squared Hz by dou Ez squared is equal to minus omega squared mu epsilon Hz. Okay. So as we all know that the wave is propagating in the Z direction. If it is propagating in the Z direction, this component Hz is reduced by the factor e power minus gamma Z. Okay. So here we can take the second order derivation for this Hz component with respect to Z direction. This can be written like this, gamma squared Hz. So here the second order derivative of this Hz with respect to Z direction is given like this, gamma squared Hz. Okay. So next we are going to move this value to this side to make it as a proper equation. So here we can write gamma squared Hz plus omega squared mu epsilon Hz. Here this value as a common one, we can take it outside. As we all know that gamma squared plus omega squared mu epsilon is equal to what? H squared. So this is important factor. From this we can find out the value of propagation constant. Okay. So next we can substitute this value over here. Then we can get dou squared Hz by dou x squared plus dou squared Hz by dou y squared plus H squared Hz is equal to 0. Consider this as the first equation. In general, the magnetic field in the direction of propagation has the values of x component and y component. So here we can represent Hz naught is equal to x and y, where capital X represents the function of x component, capital Y represents the function of y component. Then we can substitute that Hz value as x and y in the first equation. Then we can write d squared xy by dx squared. Actually the first equation is like this, dou squared Hz by dou x squared. Correct? So this is the first part. So in this one, dou squared represents the partial differentiation where Hz consists of both x and y component. Correct? So here we are going to separate x and y component using these functions. So we can use the term differentiation. So d squared xy by dx squared plus d squared xy by dy squared plus h squared xy is equal to 0. So with respect to this x, we can take this y as a constant outside. So y into d squared x by dx squared plus x into d squared y by dy squared plus h squared xy is equal to 0. For further simplification, we can divide this equation with the term xy on both the sides. Then we can get 1 by x d squared x by dx squared plus 1 by y d squared y by dy squared plus h squared is equal to 0. So now we have x term alone, y term alone, and then one constant value. So now we can move this y term to this side as a minus. We can get the equation like this, 1 by x d squared x by dx squared plus h squared is equal to minus 1 by y d squared y by dy squared. So this equation equates the function of x component and y component. Okay, so now we can equate these two components to one constant value, that is a squared. So consider this as the second equation. So 1 by x d squared x by dx squared plus h squared is equal to minus 1 by y d squared y by dy squared is equal to a squared. So in the next step, we are going to find out the values of x and y. Then we can substitute this value in hz component. Okay. So now we can take the left hand side, that is 1 by x d squared x by dx squared plus h squared is equal to a squared. Now we can move this a squared to this side as a minus. So here we can get 1 by x d squared x by dx squared plus h squared minus a squared is equal to 0. Now we can consider this h squared minus a squared as a b squared. Okay, then this equation can be written like this. 1 by x d squared x by dx squared plus b squared is equal to 0. For further simplification, we can multiply with the term x on both the sides. Then we can get d squared x by dx squared plus b squared x is equal to 0. So now we can get the general solution for the second order quadratic equation as x is equal to c1 cos bx plus c2 sin bx. Here c1 and c2 are the constant values. Similarly, we can get the value of this y component minus 1 by y d squared y by dy squared is equal to a squared. Then we can move this minus to this side as a plus 1. Then we can get 1 by y d squared y by dy squared plus a squared is equal to 0. Okay. Then we have to multiply with the term y on both the sides. We can get d squared y by dy squared plus a squared y is equal to 0. So here the solution for this second order quadratic equation is y is equal to c3 cos ay plus c4 sin ay. Here c3 and c4 are the constant values. So next we are going to substitute values of x and y in this hz formula. Then we can get hz naught is equal to x into y. X is nothing but c1 cos bx plus c2 sin bx. Y value is c3 cos ay plus c4 sin ay. We can simply multiply all the terms together. Then we can get hz is equal to c1 c3 cos bx cos ay plus c1 c4 cos bx sin ay plus c2 c3 sin bx cos ay plus c2 c4 sin bx sin ay. So here we can consider this as the general equation of the hz component. Okay. Consider this as the third equation. Next we are going to derive the field components of TE waves. Here the field components can be determined using boundary conditions. Field components means Ex, Ey, Hx, Hy. These all are the field components. Okay. So here the boundary conditions for the transverse electric waves are Ex is equal to 0 when y is equal to 0 and y is equal to b. Ey value is equal to 0 when x is equal to 0 and x is equal to a. Okay, so these two are the boundary conditions for this TE waves. Next, we have to consider the general field equations of the rectangular waveguide. We have already derived these four equations in the previous lecture video. You have to remember these four field equations of rectangular waveguide. So first we are going to find out Ex, Ey components. For that we can consider these two equations. Okay, so here Ex is equal to minus j omega mu by h squared dou hz by dou y minus gamma by h squared dou Ez by dou x. Consider this as the fourth equation. So then Ey component is equal to j omega mu by h squared dou hz by dou x minus gamma by h squared dou Ez by dou y. Consider this as the fifth equation. So this is the general field equation of the rectangular waveguide. But we are going to find out the field equations for the TE waves. What is the condition for TE waves? Ez is equal to 0. Then these two equations can be rewritten like this. So here the field equations are Ex is equal to minus j omega mu by h squared dou hz by dou y because this Ez value becomes 0. So consider this as the fourth equation. So this is the updated one. Then Ey is equal to j omega mu by h squared dou hz by dou x. Okay. So here Ez is 0. Consider this one is the updated fifth equation. So now we are going to substitute the value of this hz, that is third equation, in this fourth equation. So this hz value is replaced with the third equation. In this fourth equation, the hz value is replaced with the third equation. Then we can get Ex is equal to minus j omega mu by h squared dou by dou y c1 c3 cos bx cos ay plus c1 c4 cos bx sin ay plus c2 c3 sin bx cos ay plus c2 c4 sin bx sin ay. So in the next step, we are going to differentiate this expression with respect to y component. Here it is differentiation of cos ay is equal to what? It is equal to minus a sin ay. Okay, for this term we can get like this. If we are going to differentiate sin value, we can simply get cos plus cos. Okay, so this term can be written like this: minus a c1 c3 cos bx sin ay. This term can be written like this: c1 c4 a cos bx cos ay. So this term is differentiated with respect to y. Then we can get a cos ay. Then we can get minus a c2 c3 sin bx sin ay plus c2 c4 a sin bx cos a4. Consider this as the sixth equation. So next we are going to apply boundary condition in this sixth equation. So what is the boundary condition over here? Ex is equal to 0 when y is equal to 0, because we are differentiating with respect to y over there. Then we have to use this boundary condition. Then we can write Ex value is 0 when y is equal to 0. So in this one, sin y is equal to 0 means here sin 0, 0. Here it is cos 0. Cos 0 means its value is 1. Here it is sin 0. Y is equal to 0 means this term becomes sin 0. Sin 0 is 0. Here it is cos 0. Cos 0 is 1. Then this sixth equation can be written like this: minus j omega mu by h squared minus 0 plus c1 c4 a cos bx minus 0 plus c2 c4 a sin bx. So we have to move this term to this side. So here it becomes 0 itself. Then we can get c1 c4 a cos bx plus c2 c4 a sin bx is equal to 0. Which constant has to be 0 here? Yes, that is c4. c4 is equal to 0, then only this expression is true. Correct? Then we have to substitute the c4 value in the sixth equation to get the Ex component. Okay, so here c4 is equal to 0 means this term becomes 0 and this term becomes 0. We can get the value as Ex is equal to minus j omega mu by h squared minus c1 c3 a cos bx sin ay minus c2 c3 a sin bx sin ay. Okay, then we can take this minus outside, because minus, here it is minus. We can take it outside, minus into minus plus. So Ex is equal to j omega mu by h squared c1 c3 a cos bx sin ay plus c2 c3 a sin bx sin ay. Consider this as the seventh equation. Okay, so next we are going to substitute the second condition, boundary condition, in the seventh equation. So Ex is equal to 0 when y is equal to b. So now we can replace the y value as b over here. Then we can get j omega mu by h squared c1 c3 a cos bx sin ab. Okay, y is replaced with the value b plus c2 c3 sin bx sin ab is equal to 0. Here we can take the sin AB as a common term. Then we can write sin AB into C1 C3 A cos BX plus C2 C3 sin BX is equal to 0. Okay. Then we can move this term to this right hand side. 0 divided by anything is a 0. Then we can get sin AB is equal to 0. Then we can move this sign to this side as sin inverse, right? AB is equal to sin inverse of 0. Sin inverse of 0 is equal to n into pi. Okay. So pi, sin 2 pi, sin 3 pi. So n into pi is equal to 0. This n is the integer value. Okay. From this we can get the value a is equal to n pi by b. Okay. So we have obtained the value of a here. So next we are going to use ey term. Now we are going to substitute the third equation in this fifth equation. So what is the fifth equation? Ey is equal to j omega mu by h squared dou hz by dou x. Correct? So Hz is replaced with the third equation. Okay, the same way in the previous section. So here we are going to differentiate with respect to what? X. Okay, so this term can be written like this: minus C1 C3. This differentiation of cos Bx is nothing but B sin Bx cos Ay minus C1 C4 B sin Bx sin Ay. This term can be written like this: plus C2 C3 B cos Bx cos Ay plus C2 C4 B cos Bx sin Ay. Consider this as the eighth equation. Now we are going to apply boundary condition in this eighth equation. For this Ey component, we can consider the boundary condition Ey is equal to 0 when x is equal to 0 and x is equal to a. Okay. So first we can take x is equal to 0 condition. Then this eighth equation is written like this: 0 is equal to j omega mu by h squared. Here x is equal to 0 means sin bx this term becomes 0. Here it is 0. Then we can get plus c2 c3 b cos ay plus c2 c4 b sin ay. Okay, then we can move this j omega mu by h squared to the next side. Then the term becomes 0 as well. Here it is c2 c3 b cos ay plus c2 c4 b sin ay is equal to 0. So from this, which constant has to be 0 to achieve this condition? Yes, C2. C2 is the constant for both the term. Then we can make the C2 as 0. Do you all understand this concept? So here we are going to substitute the C2 is equal to 0 in this eighth equation. Then this term becomes 0 and here this term becomes 0. Then we can get the value as Ey is equal to j omega mu by h squared minus c1 c3 b sin bx cos ay minus c1 c4 b sin bx sin ay. Here we can take this minus as a common one outside. Then this term can be written like this: Ey is equal to minus j omega mu by h squared c1 c3 b sin bx cos ay plus c1 c4 b sin bx sin ay. Consider this as the ninth equation. So next we are going to substitute that boundary condition Ey is equal to 0 when x is equal to a in this ninth equation to get the value of b. Okay. Then the ninth equation becomes minus j omega mu by h squared c1 c3 b sin ba cos ay plus c1 c4 b sin ba sin ay is equal to 0. Then we can take this value to this side. Then we can get the 0 value as such. We can take this sin BA as a common term outside. We can move this term to this side as a denominator. 0 divided by anything is 0. Sin BA is equal to 0. Then BA is equal to sin inverse of 0. Sin inverse of 0 is equal to m into pi, where m is the integer value. So here for this b we can consider the integer m. For a we can consider the integer n. Okay. From this we can get b is equal to m pi by a, where m is equal to 1, 2, 3, etc. Okay. So now we have obtained C2 is equal to 0, C4 is equal to 0, B is equal to m by A is equal to n by B. So these four values are very important one. We are going to substitute these four values in the third equation, seventh equation and ninth equations to get the values of Hz, Ex and Ey values. Okay, so first we can take this Hz value. For that we can consider the third equation. So this is the third equation, right? So in this third equation we have to substitute these four constant values. Then we can get Hz is equal to C2 is equal to 0 means these two terms becomes 0. C4 is equal to 0 means this term becomes 0. Then we can get only C1 C3 cos Bx cos Ay. Here b is nothing but m by a is nothing but n by b. So we can get the value like this. So here Hz is equal to what? C1 C3 cos Bx cos Ay, where b is nothing but m by a is nothing but n by b. Okay. So next Ex. So for that we can consider the seventh equation. So this is the seventh equation, right? In this seventh equation, we can substitute the constant value C2 is equal to 0. Then this term becomes 0. we can get Ex is equal to j omega mu by h squared C1 C3 a cos Bx sin Ay. Here we can consider the C is nothing but the product of C1 and C3. The same way we can consider the C1 and C3 as a common constant term as C. Okay. Next we are going to find out Ey value. For that we can consider the ninth equation. So this is the ninth equation. In this equation we are going to substitute the constant value C is equal to 0, C4 is equal to 0. So here C4 is equal to 0 means this term becomes 0. Then we can get minus j omega mu by h squared C1 C3 b sin Bx cos Ay. Okay, so here we can consider this C1 C3 as a C. Okay, that is the common constant value. Next we are going to find out the magnetic field components for TE waves. So now we are going to find out Hx and Hy. For that we can consider the general equations for the rectangular waveguide in terms of Hx and Hy. So here Hx is equal to minus gamma by h square dou hz by dou x plus j omega epsilon by h square dou ez by dou y. Here Hy is equal to minus gamma by h square dou hz by dou y minus j omega epsilon by h square dou ez by dou x. So these two values we have already derived, right? So you have to remember this Ex, Ey, Hx, Hy for general rectangular waveguide solution. Okay. For these two values, we can apply the condition Ez is equal to 0, Hz is equal to C cos Bx cos Ay. For this TE waves, the gamma value is simply the phase constant. There is no attenuation. Okay. For TE waves, there is no attenuation. Then the propagation constant gamma is equal to simply the phase shift constant j beta. It has only the complex quantity. Then these two equations can be written like this. Hx is equal to gamma becomes j beta by h squared dou by dou x. Here hz value is what? C cos Bx cos Ay. Correct? Just now we have derived. We can use that value directly over here. Then this Ez term becomes 0 for TE waves. Correct? Then we can differentiate with respect to x. We can get the value as here C as a constant cos Bx. Bx means here we can get minus B into sin Bx cos Ay. Then we can get the answer as minus into minus plus j beta C by h squared B sin Bx cos Ay. The same way we can find out this Hy value for TE waves. Here this Ez becomes 0. Hy is equal to minus j beta by h square dou by dou y into hz value C cos Bx cos Ay. Okay, so here we can differentiate with respect to y. Okay, so here we can get minus a into sin Ay. Okay, so minus into minus plus j beta C by h squared a cos Bx sin Ay. So these are the field components of TE waves. Okay.